If we want to calculate the limit of a sequence using the definition, then obviously that's going to be very painful to do. So instead, we're going to have a technique called the f of x trick, which I'm going to describe now. Suppose that the limit as x tends to infinity of some function f of x converges to some number L, where for emphasis, the L is an actual real number, not the infinity symbol or anything like that. By that, what we mean is if you allow the x to become large in absolute value, what we mean by that is if you allow the x to become large, then the f of x values must get close to this certain particular number L, meaning that the y coordinates on the graph of f have to get close to L. If we make a sequence of numbers, a n, where n could be 1, 2, 3, and so on, if I choose the a sub n to equal fn, that means that the values of the a sub n numbers are actually values of the f of x numbers. And as the input into the f becomes indefinitely large, the outputs have to begin to resemble the L more and more. And since the A numbers are particular instances of the F numbers, the A numbers have to approach L as well. This is what I'm going to call version 1 of the f of x trick. So if the limit as x tends to infinity of f of x is L, and an is f of n, that means that the limit as n tends to infinity of a number n is L also. At first glance, this seems silly because it looks like I've just replaced the letter x with the letter n and the letter f of x with the symbol a sub n, but that's not exactly true. The a numbers make sense only if n is 1 or 2 or 3 and so on, and therefore taking the limit of such a thing in the usual sense doesn't make a great deal of sense. On the other hand, f of x is supposed to be an ordinary calculus type function, and I can use things like L'Hopital's rule on it. For example, a sub n could be n squared over e to the n, but only at n equals 1, n equals 2, n equals 3, and so on. If I want to know how this behaves when n becomes very large, and I want to use my ordinary calculus techniques on it, I need something that I can do differentiation and maybe integration to. So I'll think of doing only the ordinary function, f of x equals x squared over e to the x, with the idea that x can be any real number, and that I'm interested in what happens when the x becomes very large. Since both x squared and e to the x become indefinitely big as I allow the x to increase, I have an indeterminate form of type infinity over infinity, and I can do L'Hopital's rule to it. The derivative of x squared is 2x. The derivative of e to the x is e to the x. I still have an indeterminate form of type infinity over infinity, so we can do L'Hopital's rule again. The top of the fraction is now constant. The bottom of the fraction becomes indefinitely large as x increases. So 2 divided by e to the x tends to 0. The value of this limit is 0. Because of the f of x trick, this tells me that the limit as n tends to infinity of an is also 0. So the limit of this sequence exists. Also, we could say the sequence converges to 0. If I want to look at the sequence whose members or terms are given by 5n squared plus 6n plus 1, over 3n squared plus 2n plus 4, we can do as we have previously done. I'll make up a function of an ordinary variable x. F of x is 5x squared plus 6x plus 1 divided by 3x squared plus 2x plus 4. And we will look at the limit as x tends to infinity of f of x. We have an indeterminate form of type infinity over infinity, so we'll do a step of L'Hopital's rule. The limit that we're interested in is the same as the limit as x tends to infinity of 10x plus 6 over 6x plus 2, which, after we apply L'Hopital's rule again, gives us the limit as x tends to infinity of 10 over 6, which works out to be 5/3. This turns out to be typical. If I have a sequence whose terms are written as a fraction of two polynomials, if the degree of the polynomial above and the degree below are the same, which they are in this case, quadratic, then the limit turns out to be the ratio of the lead coefficients, in this case, 5 divided by 3. In this case, after applying L'Hopital's rule once, I find that I have to take the limit as x tends to infinity of the quantity 4x plus 5 divided by 1, and this is non-convergent. In the usual abuse of language, we would say that it is plus infinity. If the lead coefficients on the top and bottom had opposite signs, this would have been negative infinity. This turns out also to be typical. In taking the limit of a rational expression involving n, if the degree above is larger than the degree below, then we get failure to converge. We get divergence instead. As another example of this, let's think of the limit as n tends to infinity of 3n plus 2 over n squared plus 4. The x version of this is the limit as x tends to infinity of 3x plus 2 over x squared plus 4. Both at the top and bottom tend to infinity as x does so we'll use L'Hopital's rule. After doing one step of L'Hopital's rule, we have a constant 3 upstairs and a 2x in the denominator. As x becomes indefinitely large, 3 divided by 2 times x gets arbitrarily close to 0, so the limit exists and is 0. For this kind of limit, again, this is typical. If the degree downstairs is larger than the degree upstairs, then the limit is 0. We say that a sequence of numbers is monotonic, also sometimes said to be monotone, if either one of the two following things are true. One case is A1 less than or equal to A2 less than or equal to A3, and so on, meaning that as you increase the index, at the least, the individual A numbers don't get smaller, and they may get larger. Or A1 bigger than or equal to A2, bigger than or equal to A3, and so on, in which case the individual A numbers are either staying the same or getting smaller as you increase the index. A minor variation on the theme of this is we say that a sequence is strictly monotone increasing if A1 is less than A2, which is less than A3, and so on, and strictly monotone decreasing if A1 is bigger than A2, which is bigger than A3, and so on. These are the same as the preceding formulas, except the possibility that two successive A numbers is not allowed. For functions that are not very complicated, for example, the sequence function an, equals 2n plus 5 divided by 3n plus 7, it's sometimes possible using just algebra to figure out if such a thing is monotonic or not. In this case, I'm going to try to figure out when, if any, n values cause a n plus 1 to be less than n. It's possible that that's always true. If so, I'll know that my sequence is monotonic. It's also possible that this is never true, in which case an plus 1 would always be bigger than or equal to an, in which case my sequence would be monotonic in the other sense. It's also possible that this inequality is sometimes true and sometimes false, depending on what the n value is, and we'll have to look at that as we go along. This is a good point to reintroduce the idea of a function. In this sequence function, you're given an index, and I don't want to say the name of the index right now, so I'll just call it the index. The way you get the a number that corresponds to that index is you double the index and add 5, you triple the index and add 7, and then write the fraction down. Even if we didn't know what we were doing, we literally have a formula for a number n, so we can just write that down. But for the other one, I need to be a little bit careful. The other one, a number n plus 1, is one of the a numbers, and its index is named n plus 1. The top of the fraction is going to be what I get when I double n plus 1 and add 5. And the bottom of the fraction is going to be what I get when I triple n plus 1 and add 7. It is not known to us at this stage if this is ever true, if it's always true, or what. It is not clear to us. So let's simplify the algebra. Since n isn't negative, the tops and bottoms of all of these fractions are positive numbers. In an inequality, I can multiply both sides by a positive number without messing the inequality sign up. So I'm going to multiply both sides by 3n plus 10 and also by 3n plus 7. The reason that I'm doing this is to get rid of the fractions. Having done so, I can cancel some stuff out. Over on this side, the 3n plus 10s cancel out. Over on this side, the 3n plus 7s cancel out. So to answer the question of when is it true that a number n plus 1 is less than a number n is equivalent to solving this inequality. Next, we'll do some more algebra and see what we get. Carrying out the calculations, we find out that the condition that an plus 1 be less than an in the end is equivalent to the statement that 49 is less than 50, and that statement is true no matter what n is. So an plus 1 is always less than an. The a sequence is strictly monotone decreasing. As a second variation on a theme on the f of x trick, if I have a function f of x that gives me back my sequence terms when I put whole numbers into the f function, and if the f function is decreasing, that means that the a sub n plus 1 number must be smaller than the a sub n number. The reason for this is if f is decreasing, as I go from left to right on the graph of f, the y coordinates have to decrease. On the other hand, when x is 1, I'm supposed to get back a1. When x is 2, I'm supposed to get back x2, and so on. So if all of the y coordinates on the graph of f are decreasing, that means in particular, this number has to be higher up than that one, and that one has to be higher up than that one, and so on. If the f were increasing, that would tell me that my sequence is increasing. So another way to investigate the sequence 2n plus 5 over 3n plus 7 is to look at the function f of x equals 2x plus 5 over 3x plus 7. In the original sequence, n could take on values 1, 2, 3, and so on. So I'm only interested in x's that are compatible with that range. So I'll only look at x's that are at least 1. If I can determine that this f function is decreasing on that interval, that'll tell me that the a numbers are decreasing as well. And if f were increasing, that would tell me my sequence increased. In Calculus 1, we learned that increasing or decreasing is described by the first derivative. So we're just going to do the derivative of f and see if we can't observe that it's negative if x is at least 1. Using the quotient rule, we can easily figure out that the derivative of f is the fraction with negative 1 above and the square of 3x plus 7 below. Because x is at least 1, 3x plus 7 is positive. The square of a positive number is positive. Negative 1 divided by a positive number is negative. So this tells me that if x is at least 1, f prime is negative, f is decreasing, and therefore our sequence is decreasing as well. And we're going to say that a sequence is bounded if there's a closed interval in which all of the sequence terms lie. All I mean by that statement is there is some actual honest to goodness number that I'll call alpha for convenience, and some other number beta, so that each one of these a numbers is between alpha and beta. So maybe a number 1 is there, and possibly a number 2 is there, and a number 3 is there, and a number 4 and 5 are there. When I say that a sequence is bounded, I just mean that if you look at all of the numbers that make up the sequence, A1, A2, so on and so forth, there's a number alpha below which there aren't any of these A numbers, and there's a number beta above which there's not any of these A numbers. As an example of this sort of thing, think of a number n as being sine of n radians divided by n, where n is 1, 2, 3, and so on and so forth. One of the things we know about the sine function is that no matter what you feed into it, what comes out can't be bigger than 1, and it can't be smaller than negative 1. Since n is positive, I can divide through on both sides by n. Since n can only take on values 1, 2, 3, and so on, 1 over n can only take on values 1 over 1, 1 over 2, 1 over 3, and so on. So it certainly must be true that sine n over n is certainly not any bigger than 1. Negative 1 over n are the negatives of these numbers. You would have negative 1 over 1, which is negative 1, negative 1 over 2, which is negative but less far away from 0 than negative 1 was, negative 1 over 3, and so on. None of those numbers are further to the left of 0 than negative 1 is. So just this inequality by itself shows that the sequence given by an equal sine n over n is bounded. Actually, you can derive a little bit more information about this. As n tends to infinity, this number tends to 0, and so does that one. This is kind of a squeeze theorem that tells us the limit as n tends to infinity, sine n over n must be 0. We could have predicted that from the start, though. Sine n never gets very big, but n does. Observe that it would be illegal to use L'Hopital's rule or anything like that. I hope that everyone's having a good day, and I'll talk to you again soon.